Hi everybody. So what we're going to look at now is what happens when we take an aromatic molecule and react with an acid chloride. Alright, now this can be a little different than you've seen before where we just used a chloride and aluminum trichloride. The nice thing about this reaction is you're simply going to replace the halogen with the benzene ring. Right? And we're going to make a bond between the benzene ring and the base of the carbonyl. Alright, so let's look at the product and then we'll go back and look at how this happens. So if you remember, with most of these aromatic reactions, we're actually going to keep the benzene ring and we're going to keep the 3 double bonds. Alright, now this is the new bond we make, and we're going to keep our carbon chain just the way it is. And if you notice, everything is exactly the same, with the exception is that we've lost the chlorine. Right? And so what happens is that chlorine adds to the hydrogen to make HCl. Alright, so that's our side product. Now the nice thing about this reaction is there's no rearrangement, so the benzene ring or the aromatic molecule is always going to go exactly where the chlorine went. You don't have to worry about any rearrangement, anything else happening. It's going to switch places with the chlorine. Alright, so let me show you what happens. So in step 1, don't forget that even though they're not shown, the chlorine has three pairs, lone pairs, and the oxygen has 2 lone pairs. Now aluminum has an empty p orbital that these electrons can push into. And so what happens is, if we do that, the electrons actually come from that bond between the chlorine and the carbon. So what it produces is an aluminum with 4 chlorines. Right, so it gives the aluminum a negative charge. Forgot my L for the aluminum. Plus, and more importantly, this is the part we use, is we create a carbon that would typically be a carbocation. Except, this is the key part why we don't see a rearrangement, is these lone pair can actually push down. And what that leads us to is a carbon with a triple bond to an oxygen, and it gives the positive charge on the oxygen, but it gets rid of our carbocation. And when we talked about resonance, you might be saying, well, it's better to put a positive charge on the least electronegative atom than something more electronegative, like the oxygen. The difference here is, if you look at the carbocation, we're violating the octet. If you look at the structure here in red, everything has an octet, and the octet trumps having a positive charge on the wrong atom. So while this isn't a great structure, it's still a really good one because everything obeys the octet. And it still makes this carbon such a good electrophile that our benzene ring can still come in, so the electrons from the benzene ring can still hit here and then push those electrons back up onto the oxygen to give us our product. Right, so then after we do that step, we have our benzene ring. We've lost one of the double bonds. And now what happens is the hydrogen that was there, so let me just draw it in blue, can eliminate, reforming our double bond, giving us our product. Alright, and so the thing I want to point out is this is the key step here where the electrons can push down, because since it stabilizes this carbon, right, and gets rid of the carbocation, it allows us to avoid rearrangement. And so essentially, if you want to add a linear chain, this is the method you have to go to. And we'll talk a little bit later about tethering this to some reduction if we want to get rid of the carbonyl. Alright, let's try another one. Same idea. We know that we're going to replace this chlorine with the benzene ring. So let's just draw our benzene ring just the way it is. And now we'll keep the carbon chain just like it is in our starting material. We keep the carbonyl, and we get HCl as our side product. And remember, we don't see the aluminum trichloride in our product because it's a catalyst, right? It's used to rip off this chlorine and activate it, right? It makes this a better electrophile by pulling off that chlorine and making that carbon and carbon-oxygen carbonyl into a better electrophile, right? By being electron deficient. All right, hopefully this helped.